So, yeah, dear colleagues, today we have a presentation of our colleague from the University of Ljubljana, Faculty of Social Sciences and Center for Methodology and Social Informatics, Luka Kronegger. So, Luka, please.
Okay, thank you. So let me start with sharing the screen. And just, okay, before I start, let's just say a few words. I don't know if you managed to catch anything, what's happening around here. I'm a little bit tired at the moment. We had a great storm in Slovenia, so basically 2/3 of the country were kind of affected. So we have quite, serious situation around, well, just even if we didn't work on a train to help people around, it's kind of exhausting to follow everything and just. So this is disclaimer number one. Yeah, it's okay. We are all okay. Let's say, it's just yeah. Another thing is preparing for this talk today. Last year we had summer school, and I think we covered these topics in 2 days.
Yes.
Now we have 1 hour, so it's really, really difficult for me to squeeze this huge topics into just brief presentations of what can be done. So I'll try to do things. I shared the link to the slides. At the end of the slides, you also have some links, 2 links to the R code that you can see. I won't show you any practical things. I don't think we have time for it. But after that, you can maybe just try it on your own and maybe play around with data. So basically, I will just try to present you the. Well, anyway, 2 methods that you see how things are. Let's go. We don't have a lot of time, so let's move on. I will share may I get a permission to share the screen?
Yeah, Alina, can you please make it? I thought that it is already done.
Yes.
This ANR-Lab is someone who is ruling actually all the meeting.
Okay, still.
This is Alina. So Alina, can you can you allow to share the screen? Yeah, probably there were some problems and you became the organizer somehow.
Okay. Now I'm the boss.
Yeah.
Let me just see what. Let's say that I'm sharing this. Okay.
Yeah.
I guess you see the presentation here. I will just start with not in presentation mode because I would like to zoom in for some things at the beginning. Then I will move to presentation mode. So anyway, I was asked to talk a little bit about stochastic approaches to network analysis. As I heard, you kind of covered quite a lot of methods already, and this is why I decided to talk a little bit about 2 approaches like exponential random graph modeling and stochastic actor-oriented modeling. I will kind of put these 2 into context of other methods that are available. So let's start with an introduction. This is why I wanted to have yeah. So when we deal with network analysis, we have to have in our mind that this is okay, let's say this way. When we do the stochastic modeling of networks, this is kind of the final step in the analysis. So the idea is that we know our network very well. We have to kind of cover practically other methods that you probably learned about recently, and to be able to do the statistical analysis of what is happening within the network. So this is just like the starting point. So where the stochastic approaches to network analysis are, a few years ago I made this mind map, trying to kind of see what we have in network analysis. And let's say that we have, okay, like deterministic approaches to network analysis. Okay, we have some theoretical methods in terms of network analysis, and then we have like stochastic and model-based approaches to network analysis. In terms of the deterministic approaches, we have, let's say, the global properties of the networks in terms of the size of the network, density, centralization, distributions, transitivities, and so on. So there's global properties, and we have some local properties on the other side in terms of degree centrality, closeness centrality. So centrality is clustering coefficient for each node unit of analysis. We can talk about structural holes, dyad census, triad census, and so on. And in between, we have a different methods dealing with connectivity and community detection methods and so on. So, these are all more deterministic, actually descriptive ways of dealing with networks. So we have a network, and we find properties of units in the network, nodes, or properties of the whole network, or relations, and so on. Now on the other side, we have stochastic models, where all the knowledge from above comes in play, and we have to use it and somehow apply to it. In stochastic approaches, as we said, like the model-based approaches to network analysis, the idea is that we have some theory behind. So we are not just describing networks, but basically we have to think of the processes that are forming networks, and based on some ideas, some theories, sociological theories, we can then test some hypotheses on if this is actually present within the network. We'll talk about this later. So here, just a few of the things that are available, maybe in terms of static approaches to network analysis. So this means that we have just like one measurement of the network. Compared to some older mind maps, here is QAP that I added, quadratic assignment procedure. This is kind of the older approach. This was kind of substituted by ERGMs nowadays, but I think it's kind of fair that it appears here in the mind map. So I won't be talking about it because ERGMs can do everything that QAP methods can. So we'll talk about ERGMs. And then we have networks in time, so networks that change through time. And here we have two different approaches two different divisions that we can talk about. One is kind of division according to theory, where we have actor-based model, like the SIENA wise, and tie-based models, like ERGMs. So, you know, we have in the actor-based models, we are modeling how actors in the network behave. They decide how they decide on do they make a tie or not. While in tie-based models, we are actually looking at if a certain tie is present or is not present. So not really behavior of units, but we're actually looking at the patterns in the network. And then we have division according to measurement. So we can have like sectional data. So this is panel data, or we can have timestamp data. Cross-sectional means that we have like measurement of the network in a certain time point. We have like whole network, and then we have, I don't know, in next year we have the whole network again, and next year we have the whole network again, or something like this. In timestamp data, we have timestamp for every change in the network. So if we looked at the network of phone calls, you have like a timestamp of a phone call when the person A called person B, and when the person B called person A, and or person C, and so on. So basically you have timestamp for each event that happens in the network through time. So these are like, you know, 4 different things that we have to consider. And here are some basic models that are available for this. So according to measurement, we have like the panel data and timestamp data. And on the theoretical approach, we have actor-based models and tie-based models. And tie-based models, these are kind of ERGM data. And here we're talking about dynamic networks here. We talk about tERGMs, like temporal ERGMs, in cross-sectional data, in stochastic actor-oriented models like SIENA. While on the timestamp data, we have dynams, like the goldfish package, for instance, in R, and relational event models that are kind of the tie-based, the ERGM-based models. So these are 4 different approaches to deal with networks in time. So what I'm going to talk today about is ERGMs. We start with ERGMs, and I'm going to talk about stochastic actor-oriented models. Okay. Now we can move on. This is just something that was left out from previous years when we also had practical work. At the end, as I said, I have links to practical works, and this is just the repository of some data that you can play with if you ever want. Okay, let's talk about ERGMs. Let me view mode. Do I have like presentation mode? Here it is. Okay. So what are ERGMs? These are statistical models for network structure, permitting inferences about, you know, how network ties are patterned. So we are talking about patterns of network ties. The idea is that we have to observe and understand how the network structure that we see actually appeared. So, you know, the idea is to find kind of underlying processes, why the network looks as it looks at a certain point when we measure it. You know, it is important to know that whenever we are dealing with network analysis, when the network is already measured, when we get data, this is something that happened before. So, you know, when you measure it, it's the real network in real life is probably already changed. So we have to have this in mind, that what we observe right now is something that happened in the past. This is one thing. And another thing is that the networks that we observe at a certain point did not just come somewhere from nowhere. Basically, they're consequences of.
Dear colleagues, can you please turn off your microphone?
So basically, the network that we can observe right now is a consequence of some underlying process, that created this network. Okay, so tie-based approach is ERGMs do not model individual outcomes, so we have to be aware of this. But we are modeling, trying to figure out the presence of a certain patterns within the network. So there is rationale behind the ERGMs. So if we have a network,
I'm sorry.
Yeah, it's okay.
Luka, as an organizer, probably you can block.
I'm trying to find
this is the
right.
Aruna. This is Aruna. Yeah. So
I'm just trying to find the command where. Aha, here it is. And mute. Okay, I just muted.
Thank you so much. Sorry.
Yeah, it's okay. We all went through this.
We all have kids. I would say.
Okay, so let me go on view. Okay, so if we have a network and they're trying to talk about a specific tie within the network, this is what ERGMs do. So network ties can be explained. So how? We can explain these ties with attributes of the sender and receiver nodes. So what are attributes of sender-receiver nodes? It can be a gender of a sender or receiver. It can be age. It can be, I don't know, number of publications, whatever. It can be explained with the structure of their local network neighborhood. What is this? This can be the degree of actor. This can be clustering coefficient of the network. So this can be different things. So it's like the structural properties around a certain node that can be used. Here we have some flexibility regarding the local part, neighborhood part of the network. So what we shall actually use in the model and try to work with. So maybe again, what are the ERGMs? They're statistical models that express how different factors contribute to probability that network ties is observed. So that's the idea. And we can have like structural, individual, contextual factors. ERGMs aims to assess the effects of various network configurations surrounding the tie on the probability that the tie is present. So we are modeling the presence of tie. Okay, so this is the important issue. We're not modeling actors, we're modeling the presence of a tie. And the simplistic summary number 3, ERGMs are kind of logistic regression where the dependent variable is the odds of a tie being present. Explanatory variables are statistics presenting the structure of the network around this tie in question. Okay, here we have some asterisks. All these apply to the basic model. When we talk about temporal ERGMs, when we get to Bayesian world and so on, ERGMs, I'm really talking about the basic ERGM here, which extended beyond limits of, sometimes reasonable thinking of, what people are already doing with these models. Okay, why should we use ERGMs? okay, dealing with network analysis, we all know that's why we are using it, because there is nothing independent in our data. You know, the basic idea is that we have interdependence, which is in our normal statistics usually said, okay, everything has to be independent when we use our methods. Okay, so we have interdependence between actors, we have interdependence between ties in terms of dyadic dependence, Markov, social circuit, and so on. So, you know, the idea is that we have this interdependence between our units of analysis, and there are different kinds of and maybe let me just say again that, you know, when we start doing modeling, the important thing is that we think about sociological theories behind the processes that build our networks. So this is like, you know, the most important thing. So if we stay on, if we start with dyadic level, what are the basic things that we can talk about? It's reciprocity. In social, okay, people are social beings, you know, we are seeking for reciprocity. Okay, the homophily, birds of feather fly together and blah, blah, blah. So homophily is the second thing that is building our community. If we look on, and there are more. If we go on triadic level, we have the balance theory, the clustering, differential clustering, structural holes, blah, blah, blah. So a lot of different theories. This is just like the starting point when we talk about what is building our networks. And, you know, it doesn't matter, is it on individual level, on the network level, on the organizational level, or whatever. There are a lot of theories that can be used for building, you know, to explain how the structure emerge within the networks. So maybe here are some theories, and, you know, yeah, well, the listed ideas of what is actually, what are the factors and elements that are building the network, in terms of yeah, okay, we have here on like network self-organization in terms of activity, popularity. So this is in degree, out degree, reciprocity, closure, brokerage. Then we have actor attributes that are important in terms of effects of sender, receivers. So, you know, these are things, and effects of sender and receiver together. This is like similarity between actors. Then we have exogenous factors, like other networks. If we talk about friendship, then another variable, another network would be, for instance, proximity, how far away people live. Oh, this is already spatial factor. Then we can have other networks that we can use. If we talk about collaboration, it can be similar, some kind of similarity in terms of papers or journals that we already published in or something. Let's move on. So here is some meta theory, what to talk about. Social networks are locally emergent. What does it mean? It means that, you know, if it's always individual actors that do things, and all these things at the end kind of end up as a networks. So, you know, on the level of single node, okay, there is no network, but on the level of dyad, you have like an individual actor who is making a tie to another actor. On a triad level, then you can have transitivity, which also, in fact, you know, it's kind of transitivity is measured on a local level, so between three actors and so on. So it's always like something that is happening on a very small pattern, small number of units that we can actually explain with our mechanisms. Network ties not only self-organize, but they're influenced by actor attributes. Again, the pattern within networks can be seen as evidence for ongoing structural processes. This is like the most important part, this red thing. It's not what we see right now, it's what's been happening in the community before. Another thing, multiple processes can operate simultaneously. So it doesn't matter that if we are talking about, for instance, preferential attachment, like the degree popularity, that this is the only mechanism that is happening. You know, it can be some other thing, some other variable that is actually building up while working at the same time as a preferential attachment. Social networks are structured, yet stochastic. So, you know, when we look at these small patterns from far away, there is really a lot of them. In this way, we can kind of start to talk about, you know, statistical properties of these little patterns. So when we talk about social processes, so as we said, the ERGMs are estimated on a single observation network. So now at the moment, we are not talking about temporal networks, but, you know, just the network measured in one time point. So basically we have like one matrix and we want to estimate something that actually was happening in longer period and ended up as this certain network that we measured. So how can we talk about, you know, social processes generating this network? So what's actually, you know, how can we say that, you know, what was happening before the time point when we actually measure it? Well, the key here is like the interdependence and self-organization. So, you know, none of the patterns that we look at a certain point did not just show up. So, for instance, here we have an example. The last tie in the triangle had to be affected by the first two that were there. You know, if we're looking at the triangle, it didn't just emerge from nothing. So, at the beginning there was one tie, then there was two ties, and you know, when you have like three actors connected through two ties, then, you know, there is high probability that the third tie will also emerge. And when we observe, for instance, a network, and we have like a lot of triangles, so three actors that are only tied by two connections, there is high probability that these two connections, actually, the first thing, you know, there is high probability that these two connections will then be closed by the third one, and the triangle will be closed. I have this on the second slide anyway. So, so we cannot, of course, we cannot distinguish between processes how things are, because we don't see how this emerged. We don't have timestamp data that we would know how each tie is formed, or when it dropped, or what was happening. It's just we can say, okay, you know, there are some processes that build our network, and, you know, let's try to interpret them from this perspective. So let's see how these things are. In reciprocity, you know, first you need to have a tie from into one direction, and then, you know, somebody else returns a tie. So then you can talk about reciprocity. In transitive closure, okay, you have like a person that is friend to a friend, and then you also close this triangle, you know, okay, in degree, and so on. So, you know, first you need to have one tie, and then, okay, if you have like more than two for in degree or so on, it's growing slowly. So again, we have to be careful, because the various processes are likely to operate in the same time. You know, here, we cannot put them apart. We're just like, well, if we are aware how the different structures are built, we can think of the processes that could have led to the certain structure. So if we're looking at a transitive triad, what are the possible ways that were there before the transitive triad was built? Look, it can be just a chain, you know, between three actors, and then it closed. It can be one very popular actor, and then you know, other actors kind of started to connect to each other. So, for instance, you have I don't know, pop star, and you have like a fan club, and that's why this connection appears. You have very active person that is kind of trying to reach everybody, and then people start to connect because of this very active person. But at the end, we have this transitivity pattern at the end, which is that we observe. So we have three different stories that we can tell here. And it's good that we kind of talk about, you know, theory, some assumptions. Okay, why, how did we get this pattern here? And one thing that we can do, for instance, if we have a lot of these patterns already present in the network, there is a chance that, you know, this will occur later. And if you have a lot of this present, there is a chance. And if you have a lot of this present, you can actually extract from the network these patterns that did not appear to be this one, and basically get the idea of what the process was when you try to interpret things. Okay, let's go to equation. I'm not going to talk much about, but how the model looks like. So this is the probability of the network X, and a certain network that we are measured, and this probability of the measured network, the presence of a certain ties, depends on its structural characteristics, and these are structural characteristics of Z1, Z2, and so on. And each of these structural characteristics have their distinct effect. So these are weights, just like in regression, the betas, for instance. So the probability, X can be expressed as a linear combination of these network statistics. It's, you know, just think of regression, and it's kind of it makes kind of sense, very easy way to understand. You know, since we're talking about logistic regression like model, everything is inside an exponent and normalized by C. What are the effects? So what are the network statistics? For example, it can be, for instance, that one is the number of ties in the network, which is density simply. Z2 can be number of reciprocated ties. Z3 is number of transitive triads, and so on. So this is a very simple statistics. So and you know, now the problem that we have to address is how do we figure out the weights from one observation, from one observed network. The thing works in a way that we start with some basic model, you know, we start with some parameters that we try to figure it out how if they work or not. And let's say that we have a number of ties, density parameter is smaller than 0, number of reciprocated ties parameter is higher than 0, and transitive triads parameter is higher than 0. And for instance, that no other statistics matters. So here the idea is that we are observing a specific tie, just this one here. So we are calculating the odds of this tie being present. So how the parameters change if this tie is present or it's not. So basically we have the same function with conditional probability of a presence of a tie against the non-presence of this specific tie. Just to see here, ZE is number of edges, M stands for mutual ties, T stands for transitive ties. So we calculate this and get odds of a presence of a tie. In our imaginary model, how do we basically interpret this? So, for instance, if with negative parameter, the ties that are not embedded in reciprocal or transitive structures are not very likely to exist. So the probability is lower than half. Ties which are reciprocated are more likely to exist because we have like the positive here parameter, and the more triads a tie is part of, the more likely the tie exists, and so on. So basically, we don't know our theoretical models. So we have to speculate on it somehow, and figure it out from the theory what will be present there. So we have some basic mechanisms that we always put in terms of reciprocity, transitivity. These are so basic social mechanisms that we put in like every time. But if we go a little bit further, if you want to make a good model and figure out how to estimate the model, it takes a little bit more work. In terms of estimation, what are the, if we look at the edges, mutual ties and transitivity, if we look at a specific certain tie, what does it mean? For instance, here we have one edge, no mutual ties and no transitivity. In between these two, there is nothing. Here we have one edge, one mutual tie at the same time, and no transitive ties. For this certain tie, we have one edge, no mutual ties, no transitive ties, because here we have a circle. And here we have a little bit more complex thing with one edge, one mutual tie, and transitive ties. Depends of how we look at it. So how do we know when the model is good? How do we know when we obtain the good parameters that we estimated? Well, if the network, the point is in simulation of networks. First, we're trying to set up the parameters, then we simulate the network from our model. And if the network that we simulated is kind of close to the network that we observed, then we say, okay, our model is okay, the parameters are okay, but we have to be careful here. Here we are observing, I don't know, number of ties, number of reciprocated ties, number of transitive triads. These are things that we already had in the model. So, we are just like observing this part. If you want to assess goodness of fit, this works for ERGMs or for SIENA models later or whatever. You're not allowed to assess goodness of fit with things that you already put into your model. So the goodness of fit would be kind of evaluated through, I don't know, geodesic distance or degree distribution or something like this. So, just have to be aware that goodness of fit is something else, just like this first view on the parameters that we obtained, and and this is it for now. Maybe just an overview of estimation processes. It depends on the package and software or whatever. Usually it's maximum likelihood. It can be MCMC. It can be basically, now we have a lot of different estimation methods available, also Bayesian and so. But main step are in a way that we get some initial values from parameters. It can be random numbers or something that we kind of estimate from some other from some other models. We generate random graphs under the current parameter vector, update the parameter values by comparing the distribution of graphs according to the observed graph, and then this run as many times as possible until the estimates converge. So this is our estimation process, and this is how ERGMs work. Okay, since we don't have a lot of time, let's just run through an example. This is example published in, well, it's a paper by Luka, Koskinen, and Robbins, and it's communication network in a company. Basically, on 38 employees, we have network of communication between nodes. Tai is another executive with whom it was important to communicate to get work completed. So basically, we have binary directed ties. And there are some additional attributes in terms of experience. So number of project actors have been involved with, level of seniority, and office membership. So we have some individual attributes and dyadic attributes. These are other networks that are also measured on the same data. And this is advice network. So with whom actors, from whom actors receive advice. So basically, what we can see, our dependent network is communication network. And then we have our independent network, which is like advice network. And then we have additional attributes on the actors that we can use in the model. I will just run through this. This is important communication ties. This mutual communication. So this is bidirected ties. Then we have important communication ties, which node size is set by number of projects each actor had. And here we have seniority. And then we have office membership, so different departments. As I said, I don't want to spend too much time on this. I just want to show you technically how the results look like. For instance, arc. So this is our initial edge. This is kind of the baseline for each model. So it's the presence of a tie. Usually the parameter here is negative. This also holds for SIENA. So when we talk about density or just edge parameter, it's usually negative because of the cost of each edge the person has. So you cannot be connected to everybody in the network. Okay, then we have like reciprocity, we have in degree popularity, we have activity, which is out degree, simple two path. Remember when I said that the two path is the baseline for the transitivity. So basically this pattern here is like the baseline. If it closes, you can get a transitive triangle. So this is kind of the start. If you have a lot of this, then there is a high chance that you will also get a transitive triads. Then we have multiple two paths which is kind of the similar thing, just you know, connecting two actors through the list of the third actors. Then we have like different kinds of transitivity and cyclic closure. So these are just purely structural effects. So this is just the structure of the network. The next one is actor relation effects. So we have some attribute here in terms of, I don't know, sender seniority, sender in terms of projects, receiver seniority, receiver projects, homophily. This means that that, for instance, you have like the same seniority and the similar number of projects. Homophily office, it means they are from the same office and so on. So we have different parameters that you can include and actually test the significance of their presence, if they're significantly present within the network as a structural effects components. Here we have, if you remember, covariate network, where we have like advice network, and this is also significantly affecting the connections, communication connections. Okay. This is the convergence statistics. So basically, in terms of convergence, you need to have significant. Well, basically, you need to. It's basically a t-test, and it has to be significant. So if all this is significant, then you can say that the parameters are okay. Let's just look at the whole model. This is like the whole model when we have like the reciprocity, two paths, and all these parameters in, and you know, the overall project that could be, well, the overall results in terms of communication network, what is affecting the communication. We can see that we have, like, for instance, reciprocity significant, popularity activities negative, yeah, which means that it's not so activity is not connected to for forming more ties and so on. So let's, yeah, sorry, I think I'm hurrying too much. Okay, we are moving to the next topic. We can make a 2 minutes break if it's okay with you.
Sure.
Yeah. Are there any questions so far?
Yeah, colleagues, do you have questions? Actually, I would just go to the previous slide and ask about kind of substantive explanation of what we get if we look at this table.
Yeah.
Yeah, you started discussing. You was telling a little bit that reciprocity is important, and so what else can we say here? So we have, for example, seniority. Also, I see this is quite a high number, but it's not so high. Yeah, and path closure. So we have all the parameters here, and what can we say? What actually is important for the network construction?
We can, okay, you know, just to be on safe side, and in a way, we know that there is a reciprocity is a normal thing for the network generation. So people who talk to each other, you know, they talk in both directions. It's not just when they said they need to talk to somebody to do something important to finish the job, when they discussed it with somebody, it was actually mutual. They were mutually mentioned. This is something. Okay, this is the reciprocity part. In terms of, for instance, in two paths, you can see that it's not it's not significant. So basically, we can say that two paths are maybe somehow not detected as a forming mechanism for the three paths, and we have cyclic closure is definitely not the thing within the network, and the path closure it is. So basically, we have I would say the names here are a bit strange, but I think this is the transitivity, the path closure. So we have the transitivity significantly present within our network. Okay, so as expected, but the cyclic closure is not the thing. Then if we look further, obviously interaction with seniors is significant. So obviously the seniors are well, probably they're leaders of the networks, holding network together in a way. It would be if this wasn't true, this would actually mean that you have some structures within the network where the seniors are not actually leading the company or something like this. So it can be used for detection of when you have like the formal structure and informal structure, and it may happen sometimes that in some companies that informal structure kind of is leading the dynamics within the company, which is not necessary a good thing, especially when we talk about, for instance, advice. So there could be also the connection in terms of, okay, to whom are you going for advice? Are you going to the seniors, or are you addressing people who are basically not so established or something like this? So these are somehow expected results in a way. So nothing strange is here, but it's yeah. Okay. Let's just move on and tell a few things about networks in time. So everything that I told you right now still holds for stochastic actor-oriented models. Okay, so we have to think about the processes that are happening within the network, and that we are going to test them against something. And at this time, so far in ERGM, we only had one network at one time point, but now we are looking at the networks in several time points. So basically, we are going to model the changes within the network in time, and the networks that we are the parameters that we are going to estimate are going to we are going to model them and compare them to the first network. So we always compare it to the network in time in t-1. Okay, just yeah, let's slowly go to this way. So let's start with some terminology. When we talk about stochastic actor-oriented models, it's a very long term, and let's slowly go through it. Maybe the first thing to mention here, what was Control Shift. Now I have it. So the first thing when we talk about stochastic actor-oriented modeling, it's SIENA that comes to our mind, and this is the program in which one of the first. Well, it was the most important in terms of development of this method. And SIENA stands for Simulation Investigation of Empirical Network Analysis. It's the software in which method is implemented. The key figure here is Tom Snyders, who basically built the whole story about SIENA. Our SIENA is the R version of SIENA. So just have in mind, it's been implemented in R since quite some time, and it's really nicely documented and everything. So it's really nice program to be used if you have appropriate data for it. Now again, the method SAUM is applied on data when you use R SIENA. There are a few different types of models which are referred to as stochastic actor-oriented, but usually we just say SIENA model. It goes better from the tongue. So SIENA models are agent-based actor-oriented model. Remember, before we were talking about patterns. So we were talking about like triangles. How many triangles do we have in a network? How many mutual ties do we have in a network? So it was always, we are focused on ties. So how many of these types of patterns of ties are present? Here we have actors who are the focal. So this the SIENA models model the chain of unobserved network states between two observations. Remember, we are at this point, we have like network in time 0, and we have network in time 1, or time 1 and time 2. And we don't know what happened in between. So what we are modeling here now, we are simulating the sequences of the smallest possible steps in a network change. So, how to come from network in time point 1 to network in time point 2. So we have to figure it out all possible ways to come from one network to the second one. And we do this through something called mini step or micro step. So basically we're simulating each and every tie change that brings us from network in time 1 to network in time 2. Then we compare the results of simulations to the observed data at time 2. So, similar way as we had it in ERGMs. We have to optimize model parameters in a similar way as we did in ERGMs. We just have some other things to cover, because now we are dealing with actors, not with ties. Anyway, each simulated chain of network states represent what could have happened to the network and how the network could have evolved between time 1 and time 2. This is what could have happened is the thing that we are going to talk about. So the heart of the model is mini step. In each step of simulation of a network changes, an actor is chosen and prompted to make one change in his or her outgoing ties. So basically, we have, remember, we have network in time 1, and we choose one actor randomly, and we ask this actor, okay, please do something, make a tie, drop a tie, or do nothing. So this is like the different things that actor can do. Basically, here we have a multinomial choice in way of to whom you're going to do this change. Okay, what determines which what actor will do? This is actually very similar to what we talked about before. We talked about, the actors are choosing according to the network structure around actor. This is our ego. According to attributes of ego. So, me as an actor, if I talk the gender, it can be gender, it can be age, it can be whatever. I will decide upon the attributes of others, so about alters. So if I want to connect to senior actors, I will choose the senior actors above the younger actors or something like this, or any combination of the above. So it can be attributes of alters whom ego is tied to in the network. So this can get kind of quite complicated combinations. These factors can affect side changes by actors. And the question is, yes, how exactly? So how does my current set of friends affect my friendship choice in the next moment? Here I have an example. We have a variable which is the network, like the friendship network, actor attributes. So this is, for instance, gender. And then, we have to figure it out how these attributes will affect the changes, how I choose to form or do whatever in the network. So how does gender affect the whether I like someone, like Bob, or not? So whose gender? Is it my gender? Is it Bob's gender? Is it our gender? So is it the same, or so mine would be like ego gender, Bob's will be the alter gender. Both is like, do we have the same gender? The number of my male friends. So if I have a lot of male friends, will this affect my choice towards Bob? The number of Bob's female friends or male friends, does this affect my choice? The number of male friends that we have with Bob. So look, here we just had like two actors and one variable, simple variable, which is gender. And these are all different variables that we can include our model that can affect choice of me as an actor towards Bob. Yeah, so just bear in mind that these are different mechanisms that can form our network, our choices in the network. And the idea is that we figured out, that speculate, or that we have some theory what are the things that affect the choice, and then model this and use this in SIENA model. So so how do we put this into model? Gender of ego, gender of alter, same gender of ego and alter. Remember, this is what I mentioned before. So this is how the SIENA models are specified. We have a specific operationalization of a variable which affects actor, and yeah, depends on alters and all other different attributes that are measured within the network. Let's move on. An effect is okay. Let's just move here. So each effect, just like before, has some kind of weight that we have to estimate, the parameter, which tells us if actor prefers a higher or lower value of the effect statistics. So just like similarly as in ERGMs before, positive significant values, it means that for instance on the I don't know, alter that I prefer others being males, then it means that I inclined towards having alters as being males or females friends. Okay. How do we estimate appropriate effect weights? Again, we simulate networks and do this as long until we get some stable result. And again, the networks are simulated and compared to the measured networks that we want to reach. Maybe it's just some examples of structural effects. For instance, here in terms of reciprocity, here we have the tie from in our matrix. For instance, friendship network are our actors, and this is tie from I to J, and there must be also tie from J to I. So basically, we're just summing up the number of reciprocated ties in the network. We are just summing up number of transitive triplets, transitive ties, 3 cycles, and so on. So the effects are relatively simple thing that we can calculate. And if we look at the tendency of girls to send ties, receive ties, and the tendency of actors to have the same sex ties, we can make, for instance, this is the VI is our variable on gender. So let's say that 0 would be for boys and 1 for girls. So basically here we just calculate out degree and multiply it with 1 for the girls. So basically we get the weight here as a number of ties that girls sent out. Here is VJ, so this is the receiver. So number of ties to girls. And here is the number of ties if gender of sender and the receiver is the same, and we kind of some number of ties towards, well, of homophilous ties. So the effects are technically relatively simple, but we build them together later. So when you open for instance, the SIENA manual, you will see something like this, where we have the effect with beta as a weight of effect and S as the effect statistics. This is something that we had up here. These are effect statistics. And K is the index of effect. So basically, this is actually every effect has a number. So basically, you can quite simply find it when you're building up your model. Let's not spend too much time here. Again, we are calculating probabilities to change the network to a new form, and compare it well, basically we're calculating odds again. That's maybe just for example, again on the level of choice. Before, when I talked with ERGMs, I talked about presence, how the odds of presence of a tie, comparing to we compared the whole networks and calculated odds of presence of a tie. Okay, now at this point we are modeling the behavior of actor. So we have this xi, the ego, and we are going to model the choice of an actor. So it's when an actor is selected to be able to make a choice, the actor can create a tie, dissolve a tie, or do nothing. So with the situation that we have here with Christoph and Zsófi, we already have reciprocated tie. Christoph can do what? Can create tie to pair, because he cannot create a new tie to Zsófi. He can dissolve tie to Zsófi, or do nothing. This is the third option. So what's, you know, and if we build up our model, so let's say that Christoph cares about not having too many friends. What would this mean? That out degree would be a negative, so I don't want to have too many friends. Reciprocity is 2, so yeah, I still want to have friends. And the homophily is 1.5. It's, you know, it's positive sex homophily, and here it is. So basically, let's calculate what do we have here. So in the first choice, in the first option, Christoph is building up a tie to pair. In this way, he will have like 2 outgoing ties. This is 2. He will have 1 reciprocal tie, and the same sex ties. We also have like the we also have 1 tie to pair. Okay, if he drops a tie to Zsófi, then
Luka, I'm sorry. Can you please
yeah,
zoom out a little bit, because we do not see the whole slide, and probably there's something important.
Okay, let me just let's.
Yeah. Mm-hmm.
Okay, you see it now?
Yes.
That's strange. Okay. So anyway, basically we are counting how many different things. If Christoph drops tie to Zsófi, he will have no outgoing ties. He will have no reciprocated ties, and he will have no same gender ties, same sex ties. If he does nothing, he will have like 1 outgoing tie, 1 reciprocal tie, and no same sex ties. So basically, we calculate the surrounding state around Christoph at a certain point, and he decides on what's the most convenient for him, what he likes. We're trying to maximize his comfort in a way. Yeah. So we're trying to maximize his choice, and here basically what we do with these weights, we can calculate the best option for him, and is the best, you know, most convenient for him according to the model that we proposed would be to actually create tie to pair, and this is something that he would do at this certain point. So maybe just to make a bit of a summary, since you know, yeah, this is the first summary, because yeah, as I said, I really shortened up the presentation. At certain points in time, actors consider changing this the set of their outgoing network ties. So this is something that we are modeling. Each possible choice is described by an objective function that takes different effects into account. Here we had like out degree, reciprocity, same gender, and so on. So homophily, transitivity, whatever. The probability to change specific tie is modeled by a multinomial choice probability model, which is based on a comparison of the objective functions. So we are trying to model if the actor will add a tie, drop a tie, or do nothing, and how attractive is this outcome relative to others. So, you know, which one would be the most attractive to a certain person, considering the certain model that we proposed at the beginning. Okay, maybe just quickly how these things are in practice. The idea is that nowadays we're using our, you know, stochastic actor-oriented models in R. So what we have to do is we first have to make a list of dependent networks. So it's basically agency matrix and temporal networks built one another. So then we have to add dependent behaviors. So dependent network is our network in time. Okay, it can be friendship if we're modeling friendship. Then we have dependent behavior. I didn't even talk about it. In SIENA, we can model not just you know, the change of the network, but also the change of variables in terms of, for instance, the example, we can model if the actor will start to behave in a different way according to the network structure that he or she has around him or herself. Okay, then we can have constant actor covariates in terms of vector values. Constant actor covariates would be gender. It can be changing actor covariates, which can be what we had, number of citations, maybe in the collaboration network or something like this. We can have changing dyadic covariates. Before we had, in previous example, we had advice network, and this can also change in time, and this can affect our dependent network, and so on. So it's you know, we can build up the model and run it in SIENA and use it later for the estimation. Okay. How are we considering the time? It's been quite, yeah. We're a bit late already. Are you used to prolong your sessions?
We have a kind of 2 academic hours, which is 1 hour and a half. So it is totally fine that he is still here.
Okay, let me try to just let me see what we have. Okay, so let's look at the structure on. So what do we have here? In practice, how things look like. We have discrete measurement of the networks. Okay, so the idea is that, well, the fact is that our networks are measured in the discrete time points, and they change through time. Okay, so at time point 1, the network looks like this, and the time point 2, the network looks different. Okay, now the assumption of SIENA model is that time is running continuously. So we have continuous time model. So the idea is that through these micro steps that I mentioned before, that, you know, we are modeling time continuously. It doesn't matter how fast the time is running, but basically, you know, whatever happened within this network, it was kind of running. And the point is that sometimes some ties may have established between these two measurements and dropped at the same time, and again established and dropped. It could happen that, you know, it can be a very unstable network in some if you look at the local at this very specific time. But what we are observing is just like, you know, network in time 1 and network in time 2. So we don't know what actually is happening between these two time points, but the model is actually living between these two time points with its own life in a way. Just like we mentioned, the actor is chosen okay, to make a change, and this actor can decide according to their own preferences whether they will do something or do nothing, or they can change it if they have a chance several times, and so on, in a way that we come from network in time 1 to network in time 2. So how do we estimate these things? Well, of course, we estimate through simulations. So we have network in time point 1, we build up a model, and then we simulate networks, and we are trying to reach to the network that is as similar to the measured network in time point 2. So basically, we are building the model the way that the network evolves from network in time 1 to the network in time 2, and this modeled network, this simulated network that is supposed to be there in time point 2 has to be as close to the measured network in time point 2. Okay, it's the same idea as we had in ERGMs, that we are trying to simulate networks and at the end get to something that is as close to what we actually measured. Okay, so the algorithm looks in a way that we are simulating. So are the networks simulated similar or equal to the network 2? If it's not, we adapt parameters and go on with simulations and go on and go on, and this can take some time, but at the end, if the parameters are good descriptors of the social processes shaping the social network, if we actually get to the network that we similar to the one that we observed in statistical way, we have to say it in statistical way, then actually we can say, okay, we chose the right parameters, and we managed to obtain, well, we chose the right effects, and we managed to get to the right parameters of these models, of these effects. Okay, now there is something called rate function. I mentioned it before, that the actor is chosen to do the selection, to do something, select or drop a tile or whatever. So this is a special, this is a separate process that is actually modeling time within our model. Okay, so through the rate function, we are modeling the time spans between two subsequent changes happened within the network, when actually the pace of mini steps. Yeah, so how many mini steps happen from network 1 to network 2 that we measured. The time model can be specified with parameters. Again, we can model it that, for instance, for the part of the network, then they are more eager to do changes than other part. So we don't do this often, but if you have, for instance, okay, you get the rate parameter, the basic rate parameter you get every time that you model SIENA, and usually it's just like this, the same rate parameter for all actors within the network. But we know, for instance, that when we model the disciplines, that people in humanities collaborate way less than people in biotechnical sciences. So the rate parameter was much lower in the humanities than in biotechnical sciences, because of the whole dynamics within the network. How basically we can say that in biotech the time runs faster than in humanities, from the perspective of collaboration. So if you're aware of these differences in how time runs in different environments, this is kind of like God's way of taking care to say, okay, your time is slower than other people's, but still you can model it in a way with the rate function. Maybe let's look, we saw this before, how does estimation work in SIENA? The first, we have like 3 phases in which SIENA works. In phase 1, we have like the sensitivity of statistics of the simulated networks to the parameters is determined. So here, but actually I should mention another one. We have a pre-phase also. So because before we run the model, there is a pre-phase where we actually put all the networks and all the variables that we have, we put into SIENA object, and we run some descriptive statistics on this data. So basically, we first run the first SIENA part where our model is built. And basically there we obtain some basic statistics on how much the networks changes through time, for instance, on levels of variables, on ranges, and so on. So basically we get some general view on our data. Then when you build up the model, then this is the phases that actually happened. So in the first phase, we test the sensitivity of statistic of the simulated networks to the parameters. Then parameters are estimated by updating. It's like this changing, going up and down. It's what was mentioned a few slides. This part, and in the phase 3, we check convergence. So if the target statistics are really close to 0, so if we'll calculate. So if the differences from target statistics are close to 0, so basically here we can calculate standard errors. In SIENA, again, there is a lot of different ways to estimate the model. The basic, what we use is method of moments. But again, this method really evolved in the recent years. So there is a lot of different methods that can be applied for estimation. For basic users, I think that method of moments works more than good. Okay, then we get results. Let's see what do we do when we obtain the results of SIENA. The first thing to be known: the models that did not converge should not be interpreted. So if these numbers are not where there should be, you just don't talk about them. Okay, it really doesn't work. But okay, let's start. The t-ratios for convergence. These are the t-ratios, are deviations from the targets. The quantity, how much the simulated statistics deviate from target statistic on average. They're calculated as average deviation divided by standard deviation of so these numbers should be lower than 0.1. Okay, then there is this goes for each parameter. Okay, this is the one, and the second one is the maximum convergence t-ratio. This is just one number that you obtain at the end. It's also written in the results, and is similar as the above, but for any linear combination of the target statistics. So basically here the number has to be higher than 0.25. Okay, if the model did not converge, use the result that we obtain in this run and rerun it with, so we use the previous ans, like previous results, just put them into the model and rerun it, and maybe adapt something manually, but many times it just needs more time to rerun the model. If we use the rerun, actually we will skip the first phase, so this kind of saves us quite a lot of time, because everything is quite time demanding. Maybe just yeah, not as much as it was when we started. When I did my PhD, I managed to go to the coast for 3 days when I ran the model. Now we don't even have time for coffee. So it's a bad luck that computers are better than they were. Okay, so parameters, maybe just these parameters are estimated by simulating networks. Starting the network observed at T1, trying to reach networks similar to the one observed at T2, and so on. So basically, we are going from one network to another one, and so on. Does the simulated chains of tight changes represent likely paths how the network could have evolved between through time? The estimation optimizes fit on the target statistics of the effects included in the model. So here we are only modeling effects that we put into the model. If we did not put it in, it's not there. So that's why we have to think about, okay, which mechanisms were there. So, you know, all these models really need theory behind. ERGMs and SIENA models, it's the theory that matters. You don't just put things in, you have to know why you put them in, and if you get a significant result, you will have to explain it why it happened. You know, that's the whole story. Here the models are built with the theoretical books, not with just test and try what will work and what not. Okay, the estimation optimizes on the target statistics of effects included in the model, but the question, are simulated networks realistic in their other characteristics? So, you know, the things that are not directly modeled, what are those? So we said we calculate in degree, out degree for each actor. Yeah, we have like the homophily. We have a lot of different things that we put into the model, transitive triads and so on. But then which statistics are not modeled? And these statistics that are not modeled, we can use for goodness of fit. Okay, so it's the degree distribution. We don't model it. And this goes into goodness of fit. So if our simulated networks have like the same degree distribution, in degree, out degree, whatever degree as our measured network, then this is good. If the distances, you know, the geodesic distance is fitting, okay. If the clustering coefficient is okay, then it's okay. So, you know, it's like we have like the macro features, the global network features that we are then comparing to the measured network, because now here we were modeling the ego actors, you know, how they're behaving. But, you know, if we take the global features, we can actually compare them to the measured network. So, yeah, what are good descriptors? Let's assess goodness of fit. So the first thing that we have to do is to look at the visual expression, whether the fit is good. So, you know, we can just look at some of the networks that are all the networks that are simulated, it can be thousands of them, are stored in our object. So basically, okay, our parameters converge. So this is the first good news. but our parameters only estimated are only those who we put into the model. The next thing, let's plot one of these networks according to our parameters, our variables, and look at them. Do they look kind of similar to those that were actually measured? So we start with visual inspection to determine whether it was okay or not. Then we calculate goodness of fit function. It's also part of our SIENA. And in this, we include degree distribution, geodesic distances, triad census, and so on. And this one takes all simulated networks and plots something like this. It's violin plot. And what do we have here? For instance, this is the in-degree distribution, in degree 0, 1, 2, 3, up to 8. This is actually distribution of the simulated networks. And what we are searching for is that this p-value here, so basically this line here is the measured network, is somehow within the interval of the simulated networks. Yeah. So this is okay. It's fitted well. It has to be as small as possible, as large as possible. So the difference should not be significant. What we want to say. So it should not fall out. So this is out degree distribution. This is goodness. This is geodesic distance. So it's the longest, shortest path. And this is goodness of fit for triad census. So basically, we can look at each of the possible options for triad census if they're fitted well. And here we have number of components and so on. So if I may say just something, this goodness of fit that I have here, it's too good to be true. So it's really on a teaching data set that it's been made on. So it's something that, it takes quite a lot of time to actually be able to show pictures like this. Okay, just don't be disappointed if the figures will not work as they work here. So what's the task for you to do is basically to go back, look into the model, find things that were not put in, the mechanisms that you did not include into your model, rerun everything and test it. It's not an easy job, but it's how it works. So, okay. This is it from me. Maybe just I put here the let's see if it works. Okay. This is the ERGM script, and here is the you don't see it, of course. I'm only sharing the. Okay. These are linked to our code that you can basically just run through and look how the basic models are done. Last year we did some practical work, so basically I just used the code. Actually, it downloads the data from the web, and basically, if you install all the packages, it should work from what we have. So, if for those of you who are eager to try things, it's a starting point, something to start with. Okay, maybe for the end, when I talk about SIENA, go to the webpage of Tom Snyder's. Again, you won't see it, and look at the manual there, because that's the manual. There is really everything is written there. And it starts with the basic examples, with basic explanations, how to do stochastic actor-based modeling. And it really it's really helpful. On the web page, you have a part where you have scripts, like learning scripts for SIENA, that you can basically run from start, and you have different parts of scripts, even from building the model, preparing the data, goodness of fit scripts, and so on. So if you want to learn more about SIENA, this web page is the starting point. For the ERGMs, there is a lot of online resources, but Statnet, the program that is also mentioned in this script, if you go to web page of Statnet, the Carter-Batz group and Krenitsky group they're really building up these things, and it's well documented there also. I think, yeah, the time is over. I'm really sorry for being too fast, but it's really hard to talk about these things yeah.
Yeah, that's great. Thank you so much. Yeah, I think that it's quite a difficult job to talk about such important things as models for like two models actually in 1 hour and a half. So thank you very much, Luka. You did a great job. We have some questions. So one of the questions was in our chat, so you don't see it here. So the question was, which of these models do you think are the most innovative and, let's say, trendy right now?
Trendy.
So yeah, in trend. Yeah.
You know,
probably,
yeah, SIENA, well, that's not a nice question. Come on, you can talk about trendiness of the methods. You know, nowadays everything depends on the measurement. It's not the use of method is something that is probably defined by the data that you have available for the analysis. You know, it depends how much money you have to gather data, or the environment that you're gathering data in, what kind of data is available. So if you have timestamp data, of course it's great to use timestamped analysis, which allows some things that SIENA, for instance, does not, because you have there explicitly given what is happening in certain times, and you can model, for instance, how much time will it take for a person to call back when the person is called. You know, this is one of the examples. In SIENA, we are modeling maybe more. Yeah, you know, it's really depends of the questions, and this is very important. Maybe for students that are kind of new to network modeling or any kind of statistical stuff, it's the questions that matter. It's not the methods that we're using, and it's so because nowadays, let's say that we have a lot of data measured already, and with big data environment that we have now, where there is so many things around, you need to state a good question and a good hypothesis, and have a good theory behind what could be done and how to address some issues and so on. So these methods, I would say, both methods, both approaches that I showed you, especially SIENA, they're too demanding in terms of application to obtain good results. It really takes a lot of effort in preparation. So don't use them because they're trendy, but use them if you need them. I would say, because they're expensive in terms of how much you have to do to actually have a good results. When we ask, when you get a questions on what to use, for instance, I don't know, ERGMs are nice because they're made for a larger networks in a way, because you don't, for instance, in SIENA, the idea is that all actors know each other because they have a choice to make a tie to everybody in the network. So this is applicable on the level of class, or, you know, on the level of institute, maybe, okay. But when you get to a discipline, then things are already a little bit questioned. But when you go on the level of, I don't know, scientific system of the country, even if you have a computer that would be able to process this, you have some things that you should consider. You know, do people actually know each other? When you know, Anna, you have a question?
Yeah, Luka, thank you. Thank you for your presentation. Actually, I was a member of your class 1 year ago during our summer school. That's why I think the tempo is like quite good, because I refresh everything, and it was really interesting for me again. So my question is, what is the main difference between tERGMs, like temporal ERGMs, and SIENA models? Because I used to work with ERGMs this year a lot, and actually here we can only have, like in SIENA, 2 time periods, like T1 and T2.
No. No. In SIENA, actually, okay, the first part of the question, then I will continue. Basically, I can close this up, I think. Okay, ERGMs and tERGMs are tie-based, as I said it before. So basically, we are looking how many triangles is there in the network, for instance, or how many dyads or specific types of patterns are there in the networks. And also tERGMs are based on the same idea. So basically, we are comparing networks. Okay, when you in tERGMs, just similarly like it was noted in SIENA, in ERGMs, you're comparing the simulated network to the originally measured network, okay? And you're trying to make a model that will simulate network as similarly to one that was measured. Okay, that's a starting point. In tERGM, we are comparing the simulated network not to the original one, but to the network in time point 2. Yeah, and then network in time point 3, network in time point 4, and so on. So this is the tERGM, but we are still counting the patterns, and that's the important part. In SIENA, we are modeling the preferences of actors. So remember what the Christoph that I mentioned before was. It was actor who was chosen to make a difference. And he was actually, according to the model, was trying to change his environment around himself according to the preferences that we put into the model. He had a preference to have not a lot of friends, but to have friends, and that the gender similarity is 1.5, whatever. So this was our model that we built. So this was that was his personal choice. Okay, that basically what we did is what we do in modeling. We infer this model to all actors. So to test it in a way. Okay, if we include
focus on mini steps, right?
On the level of mini step, but we then we generalize this on the whole. On the whole transition of the network from time point 1 to time point 2. I didn't say explicitly, the example was just on on the original network and the change network. But in SIENA, the idea is that you have more measurements also.
Mm-hmm.
So more time points that you have. And when you have more time points, then actually you get more solid results.
Mm-hmm.
But there is something. The idea is that parameters don't change in time. Yeah. So if you have some process that actually is happening in some time, and then something changes in the network, and then another process is stronger, then you have to model this also. Basically, we have time heterogeneity problem, and we can include some additional variables for this part also. But the idea is that if you have more measurements, of course, you get stronger, better results. It's easier to obtain convergence also, and so on. So, you know, if you have more data, then you have well, you know, you get stronger data in a way. You know, if you don't have a lot of things to work on, but don't go on the wrong side in a way that if you have like the huge data sets that you can do everything. It's just that it has to be thought of how to look into social processes happening through time, and you know what are the mechanisms that are changing our networks through time. Not building the networks from scratch, because here we have like the time zero network that we are changing, you know. So but it can be, you know, yeah. Mm-hmm. Maybe just something that I didn't say it explicitly now because I was rushing so much. We are modeling in SIENA. We are modeling we can separately model like the building of ties, dropping of ties, and doing nothing. So you can actually have a model where you separately model, for instance, maintenance of ties, or you know what is affecting dropping of ties, because actor is we have like three things that actor can do. The actor can create a tie, drop a tie, or do nothing, and these are three different things that are actually put into the model, and you can include them into it.
And in ERGM we have only absence or presence or tie.
Yeah.
Okay, thanks a lot.
Maybe just another thing to mention. We talked about the directed networks right now. When you have undirected networks, like co-authorship networks, for instance, there is like the third function that comes in a row, that is modeling like this undirectedness, when you have like initiative confirmation or forced collaboration or something like this. So basically, this building up of undirected tie is then another process that is also modeled separately, for those of you who might consider it. So the model changes when you have undirected ties compared to the directed ties model. For instance, there you cannot have in degree and out degree. It's only one parameter for degree, and some other things that you have to consider when you have undirected networks as a dependent network. I see here a question from Daria. We get target statistics from theory or from data itself. Basically the initial statistics initial parameters are random numbers. So you basically don't need to specify them. And when we talk about, if we talk about effects, if you're asking about effects, you basically in SIENA manual, you get, just let me find literature and I will share it. Manual for SIENA. Say it's this one. And like this, and let me share something. So basically, in SIENA manual, this is something that it's on the web page. You have getting started. Here we have model elementary effects, for instance. Just for start, in terms of elementary effects, you get no, it's mathematical. Oh, for instance, here you have transitive triplets effect, and it's explained how it works out. Transitive ties effect, and it's explained how it works out. So basically, you have like really a lot of effects that are explained here, even for two-mode networks and so on. Later, there is mathematical explanation of all effects. So in a technical way, all this is here they are. When we had K, where is the? Remember when there was effect number and there was a K parameter down there? Basically, these are the numbers that you can use, or maybe it's better to use names for building up a model. So these things are there. They're programmed in SIENA. You can also program your own, but in terms of what to include, it's something that it's a lot of, well, it's the ideas of the processes that are behind. So something like this. So it's from theory that you have to find out what is the best. Well, the best is to use a paper that's been already published, and it's as a starting point. Use R scripts, where you have like the teaching materials, training materials, to play a little bit with the networks, to run some models that you can get a little bit of a feeling how things work. And yeah, then move on. You're welcome.
Thank you, Luka. Can I have the last, at least one more question? Previously you mentioned several times some things about the computational costs that you have working with this kind of models. So what is the size of the network which is kind of doable in a, let's say, regular computer, let's say? I know that you have some additional facilities at your computer, but
no,
generally,
I would say that it really depends on the model that you have, because we have to be aware that if you have a simple model, just like we have, I don't know, 100 actors and like a friendship network in a classroom, okay, which is like, I don't know, 30, 40 actors. If it's simply just like the friendship network, that is measured in 3, 4, or 5 time points, this is kind of relatively fast thing that works out in a minute or so. But when you have additional, then depends what you do. If you have dependent networks, so if you want to see, for instance, the example is the smoking behavior of students within the class. Yeah, and the question is whether those who are smoking are socializing before they started to smoke, or they were smoking and they were socializing with smokers because they were smoking, something like this. So what, that's the idea of SIENA, that you are able to disentangle the behavior from the structure, from the network. And here, when you have the behavior, you're modeling the behavior separately. This already takes more time. It's another thing that you're modeling. if you have then additional network in terms of, okay, this is the socializing network, then you have, for instance, advice network or proximity network, how far people are living. You're adding another variable in that has to be included. So there is so much more computation. So, you know, with the simple models, things works fast.
Mm-hmm.
On a relatively large networks, 500, it would work.
Mm-hmm.
But when you complicate things, things get complicated quite quickly. Mostly, for instance, from when I used also for time usually working memory becomes a problematic thing because it doesn't put things aside. Everything is in a working memory. So yeah, this is what the problem. But on the other side, you have like the multi-core support in SIENA. So, you know, at least this works well. So you don't need to just put it onto one core. It actually, you can use the cluster within the computer or several computers or so. So it's kind of built in the distributed computing thing. So it's not difficult to use.
Okay, great. Because I have a hope to make an analysis of our data of collaboration between Russian sociologists that we just finished. So it would be nice to have some advanced analysis of this data set. But this is quite large, so I think that before this we should somehow make it smaller to remove some nodes which are not kind of important or something like
How
this.
big is it?
Oh, we have about 37,000 of nodes in our network. But it can be split into time points. We have 12 years of observations. So I think it can be interesting to practice on this data set.
You know, we did some things in terms of, for instance, excluding actors who don't collaborate, or, you know, or somehow like the periphery, and some other things that we managed to basically. When building a model, you can somehow ease the model with structural zeros or structural ones, for instance. Structural zeros are those who, for instance, are not present in a certain time point. So basically you have like people in the network, but you know they are not modeled because they were not active in a certain time point. So, you know, when you say, okay, the person entered the network in, I don't know, in time point 5, then you just, okay, you have the person in because you need to have the same network all the time, but you don't model these people that are not formally present or something like this. So with these things, you can ease the data to some extent.
Yeah. We will try.
Yeah, well,
okay.
When are you doing it now or?
Not yet. Actually, it was a plan, and I even wanted to make it before the conference in Ljubljana. But yeah, we have all sorts of things to do, and research is not the first in a row, you know. So we will see.
Okay.
Yeah, so Luka, thank you so much for your time and for sharing your expertise and for these great explanations. It was a pleasure to spend time together.